Hi everyone, welcome to today's session that is on building a movie recommendation engine with Neo4j plus FastAPI. In this video, I'm going to discuss a movie recommendation engine from scratch, real graph database, 4 working recommendation features, and a live API sitting on top of it. I'm going to walk you through the entire thing, how it is structured, what every file does, and the actual query language behind it, called Cypher. So, by the end, you will understand graph traversal, Cypher queries, and you will have seen 4 real features go from an idea to a working API endpoint. So, let's get into it. What we are building today. Okay. So, a real Neo4j graph database running locally. 31 movies, 60 actors, 7 directors, 8 users, as it is a mini project to make you understand how Neo4j works. 4 working recommendation features and a live REST API built with Fast API. But before I show you any of that, I want to answer a question you are probably already asking. Why a graph database at all? Why not Postgres or MySQL like most projects use? Say, I want movies liked by people who like same movies as me. In SQL, that's 3 or 4 table joins. In SQL, that's 3 or 4 table joins. Now add they like they like the same director. Again 5 or 6 joins. Then a friend of a friend, a friend of a friend of a friend is recommended. You know. However, many hops that takes needs a recursive query, which is genuinely painful to write and read. So here's an alternative I chose, and that is a graph database. A graph database. A graph database avoids all of that. Every record called a node stores direct sorry about that. Every record called a node stores direct connections to whatever it's related to. Hopping from a user to their liked movies isn't search through a table. It is just following these links, you know, over here. That's the entire reason this project is built on Neo4j instead of Postgres. Now, this idea that is direct pointers instead of table scans actually has a formal name. And it's worth knowing because it's a real technical reason graphs are fast for this kind of problem. And the name is index frequency adjacency. Index frequency adjacency. Each node, each node points directly to its neighbors, means following a pointer, not a searching table. The cost of a hop depends on how many connections that specific node has, not on how big the whole database is. And friend of a friend of a friend becomes one small piece of syntax you will see me use in few minutes in this way. This is star. Okay. Now let's actually look at the data I built on top of this particular idea. Okay. Now here's the shape of the data I designed. 5 types of nodes. user, movie, actor, director, genre. Four types of relationships. A user likes a movie, an actor acted in a movie is directed by a director, a movie is in genre, a genre. That's the whole schema this entire project sits on top of. And this is the theory. Let me actually show you the schema alive with the real data behind it instead of just this diagram. Okay, let me come over here and let me check if my Docker is up. Yes, it is up. I'm using the community edition of Neo4j, which is a bit free for everyone. Um, okay, here we are. The database has already loaded. The database has already loaded. Let me show you a few things. I'll explain you each and every command over here. Match path, user, name, Arav, likes, movie, likes movie, Arav likes movie, directed by, director, return, path. It's same like SQL. Match means select. We write select, select to get some queries over there. Select star from users. That is a users table, and we get a bunch of records through that select statement. So match is equal to that. If you understand SQL, you will understand this too. Okay, let me run this. Now, what has happened over here? What has happened over here? This is Arav, one of the users in the dataset, and his 5 liked movies: Prestige, Dark Knight, Interstellar, Inception, Memento, all converging on one Christopher Nolan node, one shared node every movie points to. And I will explain exactly how that happened when we get to the seed file, the main seed file. Okay. Okay. Now, these pieces over here, these pieces makes the project work. Neo4j Community Edition, the graph database itself running locally in Docker rather than a managed cloud service because I wanted every part of this visible. FastAPI, the Python framework the API is built on. Official Neo4j Python driver, which is what actually connects the two, and Pydantic, that validates data shape. Now that you know the pieces, here's how they are actually organized on disk. This is the project skeleton. Okay, this is the project skeleton, which I'll show you live. Now there are 4 files inside the app. Yeah, four files inside that, but the main one is this. One is the seed file, and three configuration files at the root, and three configuration files at the root. The Cypher files lives over here, over here. This is the database connection. This is where FastAPI app plus roots. This is where the response will shape. And this is here our data set. Okay, so let's go through what each one actually does. Starting with configuration, since that's the foundation everything else depends on. Let me open the project folder for you first. This is the project folder. Four files inside app, right? One seed file and three configuration files at the root. Okay. So this is the real project already built and running. Let's open these one at a time since yeah, let me check. Yeah, let's open these one at a time. I would go with configuration first since every other file in here depends on these three getting ready correctly before anything else can run. Let me go with first. Let's go through all the important files, I would say. Let's go through requirements txt. Now over here, there are five dependencies. Yeah, five dependencies. Fast API itself, UVCon, the actual server that runs Fast API. Fast API can't run on its own. It needs something like this underneath it. Then Neo4j driver, pinned below version 6, because that version changes how connections are managed. Then we have Pydantic for validating data shapes, and then Pydantic settings, which is what reads configuration out of a .env file automatically, which is exactly the file we should look at next. And let's see what actually inside it. That is the env. Now, three values live over here. Three values live over here. The URI, the URI uses Bolt, which Neo4j's own connection protocol, built specifically for fast database communication rather than regular web traffic. The username is fixed. Since Community Edition only ever has one account, always called Neo4j, which I showed you. I think I haven't shown you yet, have I? Yes, yes, I have shown you. Over here, here. Yeah, over here when we logged in, right? And the password is the one value I actually chose myself. Now, this is .env file, and this only describes the connection. It doesn't actually start anything. It doesn't actually start anything. But the next file is what does. Let's go to Docker Compose YAML. This is what's actual running Neo4j right now. If you see, while I record this, port 7474 is the browser interface. See, browser interface. Okay, and I will use it throughout this video. 7687 7687 is that Bolt protocol for the Python driver, not for humans. And this volumes line this volumes, this particular line, is why the data survives every time I stop and restart the container. And I can prove that to you right now. The container's been running and the whole time I've been talking. I've shown you already. This is Docker Compose PS. So it's up and has been the whole time. So configurations covered. The database is running. Now before I show you the actual features, there's one more thing you need first. The query language itself. Everything from this point forward depends on being able to read this. So let's slow down over here. Okay, let me first tell you, or okay, let me show you with the help of the query and then I'll explain you this part. Right. So over here, suppose match M movie directed by the director. Suppose name is Christopher Nolan. Return M dot title, M dot year, order by, order by M dot year. Right. Now read this sentence. Now read this. I would say, okay. Now read this like a sentence. Let me open my pen over here. Now read this like a sentence. Match a movie. Match a movie directed by a director whose name is Christopher Nolan. Okay. Again, match a movie directed by a director whose name is Christopher Nolan. Right. Now read this. This is very simple. You're matching a movie which is directed by a director, Christopher Nolan. Okay. Makes sense. Now, this round brackets over here, these are what? Nodes. The circles. The circles. This square brackets over here are, it means inside the arrow. Okay. This means inside the arrow. Okay. This means relationships. Relationships. The connecting lines. Let me run this. Okay. It hasn't come that way. But okay, I'll show you in a different query. Okay, let's take this example over here. Let's take this example. Right. Again. Now, these round brackets, these are nodes. Okay. These these brackets, that is square brackets. Okay. Inside an arrow are, these are relationships. See, inside an arrow, these are relationships. See, these are inside an arrow. These are relationships. Okay. And these are like connecting lines. So what I want to tell you is that if you see this node, a thing in round brackets as a node, okay, In square brackets is a relationship. This is direction. Arrows are the direction. Okay. And rest of it, I'll let you know how it comes. Merge is something like if I am going to find something. Suppose I'm trying to find a name. If it is available, it will show me. If not, if it is missing, it will create it. Okay, it will create it. Match is like a select statement. Find a pattern. Okay, return what it gives back, the result. And where is same, the filter that we usually do in SQL. That we usually do in SQL. Okay. Uh, Let me show you in a different way as well. One more query, and that will make a complete sense. What I want to show. Okay, match you user name Arav likes movie likes other user where, that is filter, return other dot name comma m dot title. Now over here, this where it filters results. It filters results, and this operator means not equal to same symbol SQL uses. Same symbol that SQL uses. Let me run this. Okay, here. So here what is happening? Name is Arav. He likes movie. Okay, the same movie is liked by other users as well. So if Arav likes Dark Knight, Vikram also likes Dark Knight. Ananya, if Arav likes Interstellar, Ananya, Priya and Vikram also likes Interstellar. Okay, if Arav likes Inception, Vikram also likes Inception. So user is Arav, likes movie, and the same movie is liked by other users. These are the other users. These are the other users. Okay. Now let me show you relationships. Let me show you relationships. Means like I would say how to get the shortest relationship. Let me give an example over here. Now over here, star 1 dot dot 2. This means 1 to 2 hops in any direction. One query and it returns Arav's own movies and other users who share them. It's his own movies and other users who share them. Like in this particular case, if I say Dark Knight, Over here, Arav's likes, Vikram also likes. Okay. Then Interstellar was liked by Ananya, Priya, and Vikram too. Okay. Over here. And then we have Inception. Okay. So this means one or two hops. One or two hops. You will see it again. Let me be more specific by giving you a more direct example of the features. That would be much more easier for you to understand. Right now, you just try to understand that these are hops, one or two hops. That is the shortest distance. Okay, let me show you a connected example, much more easier for you to understand. Suppose match P equals shortest path. Suppose Leo actor. This is going to be much more interesting. Name Leonardo DiCaprio. Mm, star 666. Nolan director. Name Christopher Nolan. Return P. Let me see. It now over here, it says that give it two nodes. Give it two nodes. Find the shortest chain connecting them. Given two nodes, find the shortest chain connecting them. See, given two nodes finds the shortest chain connecting them. Capped at however many hops you allow. Many hops you allow. So this 6 means that it has a limit of 6 hops. Means it cannot continue forever to find the shortest path towards Christopher Nolan. If it figures it out, if there is something that is linked to Christopher and Leonardo, then it will show you. And then it will show you till 6. If it goes beyond that, it will stop. Okay, but not more than that. So this is a limit of 6 hops. Limit. Okay. So see, so far what we have done, we have learned the vocabulary. Okay, how this Neo4j works. How it is similar to SQL. Like we use select statement, we use over here match, right? Filtration is almost same by using where. Okay, so everything is similar. It's not that difficult, you know. So this is what I'm trying to make it clear. Okay. Okay, now let's go see the file that actually used all of this to build the real data set sitting behind everything I have shown you so far. Okay. Uh, Let me open the cipher. Okay. Now, this is the file that built the entire data set you have been seeing. 31 movies, 60 actors, 7 directors, and 8 users. It's already been run. The data is already sitting in the database. But now let's understand how it works. This line, match and detach, delete, n. This first line, wipe everything. This detach, delete removes a node's relationship first, then the node itself. Cypher won't let you delete a node while something's still connected to it. This line is what makes the whole file safely rerunnable. Okay. Now, right below this, before any data gets created, there is a section that makes everything after it fast. Create constraint movie title if not exist. For M movie require M title is unique. Now constraint like this one do two jobs at once. First, they stop duplicate titles and they silently build a fast lookup index behind the scenes. Behind the scenes. Okay. Now over here, this part loads all the 31 movies in one shot. All the 31 movies in one shot. Okay. Now this unwind over here till here, okay, turns a list into an individual rows. Turns a list into individual rows. This block with the real 31 movie list is how the entire catalog got created in one statement instead of 31 separate ones. Okay, ones. And then again the same thing, unwind. Again, this will turn a list into individual rows. Okay, now with this, the real actors over here, and this is how the entire again the data log got created. Okay, instead of I think 60 actors we have, right? Okay, now let me show you the feature that I built with this. Okay, the first feature was recommend movies. That is, people similar to me like Dex. I haven't seen it yet. Okay, let me show you with the Neo4j query. See, this is very interesting if you compare with SQL. Easier to get the connections. You know, in this particular way in graphical form. So let's run the first feature that is the recommend movies. Let's run it over here. Now I'll also explain you, while writing a query. Suppose match. Now by this time you must have understood, what how these nodes are connected with the relationship. If I write user username is Arav or anything, you know, in the database, if it is available, Arav, then likes, okay, Arav likes seen movie, okay, seen movie, then match seen likes uh, neighbor user neighbor user likes and recommend movie. Here it is filter so that Arav is not counted twice. Likes, then we want to return title as recommendation count. Let me write, then I'll explain you properly. Count distinct neighbor as strength. Collect means in instead of giving you separately, it gives you a list of values. Distinct neighbor dot name as recommended by order by strength limit 5. Now let's understand this first. Let's understand this first because it looks actually very dense. Now this first line, first one. Okay. Now find every movie Arav already likes. Find every movie Arav already likes. Okay. Second, for each of those movies, find everyone else who also likes it. Who also likes it. Now think of it like this. If you and I both loved Inception, you are now one of my taste twins for this query. Okay, got it. Third, follows those taste twins further to see what else they liked beyond the movie we already had in common. Okay, the last two steps, clean it up. Filter out, filter out anything Arav's already in scene. We do not want to double count Arav. Okay, then rank what's left by how many different people independently suggested it. How many different people independently suggested it. Okay, again, ranking in descending. Okay, and limit is still 5. So if it is top 5, so we are going through the descending order. Let me run this. See over here, descending order. Ananya and Priya. Okay, I like Dune. Ananya and Priya like Dune. So this is the strength. Okay, same ways for Arrival. Same goes with Blade Runner. But Ananya and Vikram, again the strength is 1 1. Okay, now I want to show you one more thing parallel to this. What I want to show you is queryx.py. Now over here, this is the, see, recommend movie. Now this is the exact same query, but over here Arav becomes a placeholder. Placeholder. Okay, by dollar sign. Filled in whoever calls that API. Is it Arav or anyone else, or me or you? Okay. And same goes for others too. Okay, such as similar users, shortest path, common interests. Okay, common interests. Now let me show you one more thing in parallel, because now this will become much more interesting and much more logical and understandable. uh, Let me start the fast API app. Python -m uvcon app.main app reload. Okay, docs. So we are talking about recommend over here. If I type, let's try this out. If I type Arav, I execute. See over here, same result. See, we have Dune strength 2. We have Dune strength 2. Ananya Priya. Ananya and Priya. We have Dune strength 2. Ananya Priya. We have Arrival strength 2. Ananya Priya. Blade Runner 2014. Ananya Priya. We have Arrival, Strength 2, Ananya Priya, Blade Runner 2014, and Ananya Priya. Understandable? Makes sense? Makes sense? Okay. Now let's go on to the next feature, that is feature 2, find similar users. Who has the closest taste to mine? Okay, closest taste to mine. So this one now asks a slightly different question than the last feature. Not what should Arav watch next, but how, but out of everyone in this database, who has the closest taste to mine. Okay, let's go back to the browser again. Okay, and now I can do one thing. But again, we are learning, right? Everything should make sense. Suppose match u colon user name gain Arav likes movie likes other user. By now it has made some sense, right? By now it has made some sense. You're understanding what I'm trying to say over here, or what queries are making sense, I believe now. Where other you return name distinct m. I'll explain you the query. Let me finish this off first. As shared movies collect m dot title as in common order by shared movies PSC limit 5. Now let's walk through this code first. Okay. First, start at Arav. Okay. Start at Arav. Find a movie he likes. Find a movie he likes. Then from that same movie, let me open my pen. Right. Now, uh, this Arav, okay, find a movie that he likes. Then from that same movie, find anyone else who also likes it. That's our other person. That's a part, the same two hop shape you saw in feature 1. The next line is a small safety check. Okay, it just makes sure we don't count Arav if someone similar to himself. We don't count Arav someone similar to himself. Okay, now here's the important part and the actual difference from feature 1. Instead of just noting that someone overlaps, we count how many different movies we count how many different movies they overlap on. We count how many different movies they overlap on. Someone who shares 3 movies with Arav is a much closer match than someone who only shares one. And this line is what captures the difference as an actual number. I'll show you. Now, right alongside it, we also keep a list of exactly which movies matched. Which movies matched. Okay. Uh, which movies matched. So we are not just seeing the score. Okay, let me show you. Let me run this query. Oh, okay, there's some problem. Let me see what is the problem over here. The problem is over here, I believe. Yeah, I think yeah. Okay, so here we are. So what I was saying is that uh, someone who shares someone who shares three movies, okay, with Arav is much closer match that than someone who only shares one. So Vikram is much closer to Arav's match. Okay, and this line is what captures the difference as an actual number. Okay, now uh, we are also we're also seeing over here in common, okay, which movies matched. Like it's not the score we are counting, it's the movies. Dark Knight matches, Interstellar matches, Inception. In case of Ananya, only one movie that matched. In case of Priya, again only one movie matched. Okay, so this is covering taste similarity, taste similarity. Okay, now if I want to show you the same thing in API docs, and we have what similar users, and I just tried out, and over here we have Rav execute again the same thing. Vikram shared movies 3, these are common. Similar user Ananya shared movie 1 Interstellar, and with Priya as well. Right, makes sense. It makes sense. So these were what are similar movies. Similar movies. Now let's get into a different feature. That is the shortest relationship path. Now things which it's going to be much more clearer because now you have understood the vocabulary behind the Neo4j. Okay. Now again, how are two things connected? Okay. So now it's not who's similar, but how is anyone connected at all? Okay. Again, let's go back to the browser and let me run this feature to give an example. Match a name. Let's take an actor name over here. Leonardo DiCaprio. Again, these are case sensitive. If I typed anything like in a lowercase, it won't work. B B name Quentin Tarantino match P equals to shortest path A, that is Leonardo. I think there's some problem. Mm, no, it is running. Okay. First, let me explain you the line. Okay. Now, over here, the first line, we just point at our two starting people, DiCaprio, Dic, right, two starting people, DiCaprio and Quentin Tarantino. Okay. The second line is where the real work happens. The second line, that is the shortest path. This path. Now, this is a built-in tool. You hand in two nodes, and it explores outward from both of them in every direction. Okay, until it finds the shortest possible chain connecting them. This thing, this particular, you can say syntax or the shortest path syntax. Okay, this means any type of relationship. This means any type of relationship direction, but give up after 6 steps. Do you remember I told you this is the limit? It won't shouldn't go beyond that. So it should give up after 6 steps. That is, the limit just stops it from searching forever. If the two people genuinely aren't connected at all. Let me repeat, limit stops it from searching forever. If the two people are genuinely not connected at all. Okay. And this last line, it's simple. Give me back the whole path, every node and every connection along the way, not just yes or no. Give me the result. Okay. And this is the result. This is the result. Two hops, two hops, two hops, okay, through Django Unchanged, the one movie that bridges them, that bridges Leonardo and Tarantino, okay, and this one has a obvious connection, okay. But here's another case. But here's another case where there isn't the connection at all. First, let me check out. Um, Match a user name Arav, again be user. Suppose this time name is Sneha. Let's take this name. So it must be in the database. Sneha match P equals shortest path A star dot 6. Again putting the limit. B return P. Let's see what happens. Okay, let me understand this. Mm. Two users, Arav and Sneha. Zero movies shared because Arav likes Inception and Sneha likes Shutter Island. So zero shared movies. Four hops, one, two, three, four, or understand in this way. One, two, three, four, four hops. Okay. Routed through DiCaprio, routed through DiCaprio as an actor. Let me come over here. Let me remove this. Yeah. Okay. Routed through DiCaprio as an actor, not a shared friend. Okay. Not a shared friend. Notice the arrows flip direction twice. One, two, one, two. Shortest path doesn't care about direction or relationship type over here. It just finds the shortest real connection. Okay. That is through Leonardo because these are routed through DiCaprio and the reason is they're not sharing any movie. They're not sharing any movie. Okay. I hope you're getting it clear over here. Again, if I want to show you an API, and if I come over here, shortest path, try it out, I'll type, because over here, mm, let me check. Leonardo, yeah, Leonardo. Yeah, this is different, right? Okay, Leonardo DiCaprio and and Quentin Tarantino. Let's see. Here's the URL. No path found between DiCaprio and. Okay, see, Quentic. This is wrong. This is wrong. It is not Quentic. This is Quentin. Okay, it's not crashing after all. It is giving an error that not found. Let's see now. Yeah, see. Two hops. Leonardo, Django Unchained, Quentino Tarantino. So path nodes. So Leonardo, Django Unchained, and Quentino. These are no nodes. Sorry, these are nodes. So these three are nodes. Okay. Path relationship acted in, directed by. These are relationships. And hops are two, one hop, two hop. Understandable, right? Understandable. Now let's go over to the last feature, that is feature 4, that is common interest. That is, what do we both like, even directly, even indirectly. What do we both like, even indirectly? Okay, let me show you with an example over here. Let's run over here. Hmm. Let me write match u1 user name out of likes m1 movie match u2 user name, now another user Mira likes m2 movie with u1 u2 collect distinct m1 as movies 1, collect distinct m2 as movies 2 with u1 u2 m in movies 1, kind of a list comprehension where where m in movies 2 as shared movies. Now this is optional. Match u1 likes likes movie directed by D director directed by movie likes. Phew, this query is very dense. Even I have to understand what I'm writing, but I'll explain you. It's not that difficult. Once you get into something, you know, put your head in, you will easily understand and it will make sense. am in uh, shared movies m dot title as shared movie titles collect distinct d dot name as shared directors. This one is much more dense. Anyways, let me explain this first. Where's my pen? See, the actual idea behind it is simple. Okay, the idea is find out what two people have in common. What two people, Arav and Meera, have in common. Okay, Arav and Meera have in common. Okay, in two different ways, right? Not just did they like the exact same movie, but also do they secretly both love the same director, even through completely different films. Okay, now the first two lines, you know, this separately find every movie Arav likes and every movie Meera likes. Two independent lists, nothing compared yet, right? Two lines separately find every movie Arav likes and every movie Meera likes, right? These are independent lists. Now this third line, third line bundles each person's scattered results into one tidy list per person. Think of it as a turning a messy pile of Arav likes this, something like that. Arav likes this, and Meera likes that. Meera likes that. Into a single list called Movies 1. Into single list called Movies 1, and for Meera, Movies 2. Movie 1 and Movie 2. Okay. Now, this fourth line over here is the one with the unusual syntax. That is the square brackets with where inside them. With where inside them. Now, this is called list comprehension. What is it called? This is called list comprehension. And it works exactly like a loop in Python, just written differently. In plain English, it says go through every movie in Arav's list, go through every movie in Arav's list, and keep only the ones that also show up in Mira's list. Okay, what's left is the real exact overlap. So this is talking about the overlap. Okay, this fifth line, okay, fifth line is completely separate check running alongside the first. It asks, does Arav like some movie by a certain director? By a certain director, and does Meera also like the same movie? Meera also like the same movie by the same director, even if it's not the same movie at all. I repeat, does Arif like some movie? Some movie. I'm not. If I have said same, I'm sorry. It is some. Does Arif like some movie by certain director? And does Meera also liked some movie by that same director, even if it's not the same movie at all? Okay. Now notice this says optional match. Okay. Yeah. Notice this says optional match. Not just match, optional match. Now this word matters. If this check finds nothing, it won't erase the shared movie answer we already found. It just comes back empty for this one part. It will come back empty. Okay. And the last two lines, And the last two lines hand back both answers side by side. The exact shared movie titles and any shared directors, even from completely different films. Okay, let's run this query live. Okay, over here. See what has happened. Zero shared movies between Arav and Meera, but a shared director. And who is the director? Nolan, Christopher Nolan. They each liked a different Nolan film, not a shared film or movie. Okay, film or movie. Got it? Understandable? Makes sense, right? If I go to the API now, again, so I think we are talking about common interests. And over here, if I put Arav, and over here, if I put Mira, right? And over here, see, same thing. Shared movie title is empty, but shared director is same. Christopher Nolan. They love Christopher Nolan, right? Makes sense, understandable, right? Right. So we have now seen all four features work in raw cipher and how they actually became real URLs anyone can call. See over here. See if I come over and do this, check the result. Makes sense, understandable, right? Understandable. Okay, understandable. Let's see what is left now. Okay, fast API request flow. Hmm. Okay. See, these four has worked together to run a cipher to turn a cipher query into a callable URL. Okay, let's have a glimpse over it so you can understand what is happening. Behind the scenes or in the background. Okay. Uh, See, our first step or the first stop is to understand how the app even talks to Neo4j in the first place. Okay, let's come over here and let's try to understand. Let's have a glimpse of it. Okay. Now, the first job is reading configuration. Okay. This setting class, this setting class, this setting class, this setting class. Okay. Now, this setting class reads the .env file, the URI, the username, the password, and turns it into a proper typed object. Now, notice the password field over here. It has no default value written next to it. Written next to it. If .env is missing or the password isn't set, the whole app refuses to start and fails loudly right away instead of failing mysteriously later on or in the middle of handling someone's request. Okay. Now the second job that is managed exactly one shared connection. One shared connection. Now right below it there is an empty placeholder called this underscore driver starting out as nothing since the app hasn't talked to Neo4j yet. The function get underscore driver is the important one here. The function now see, I think I mixed two things over here. See, what I was saying is that this is the placeholder. Okay, this is starting out as nothing. Okay, because app hasn't talked to Neo4j yet. Right, you got to this point. Now this function get underscore driver, uh, this one, it's an important one. Now every time it's called, it checks does the connection already exists. If yes, just hand back the same one. If no, build it once right now and remember it for the next time. Make sense? That's what stops the app from opening a brand new connection for every single request. And then, that would be slow. Okay. That would be slow. Now, the third one is The third one is actual the, I think I have missed something. No, the third one is actual running the queries. That is this one, run query. Okay. Now this one function, every route in the entire app calls. It grabs the shared connection, runs whatever cipher gets handed to it. Okay. See, it grabs the shared connection and runs whatever cipher gets handed to it and converts the raw result into plain, easy to use Python dictionaries. And converts the raw results into plain, easy to use Python dictionaries. Okay, understandable. Now, next, where do the actual cipher queries this function runs comes from? Where do the actual cipher queries this function runs come from? Okay, uh, I think you have already seen this file throughout the video. You've already seen this file throughout the video. That is queries.py. Okay, every query behind the four features: recommended movies, similar users, shortest path, common interests, right? Now, over here, as I told you, I think I have already told you before that every query behind the four features, every query behind the four features parameterized with a dollar sign placeholders instead of hard coded names. And once a query comes back with results, something has to guarantee they are shaped correctly before they go out to whoever calling the API, and that's the models.py. Okay, now we are talking about the shape, that is the pydentic, right? Pydentic. Now this file defines the exact shape every response must have. If the cipher query ever returned the wrong type, the fast API would catch that mismatch immediately. It would catch that mismatch immediately. Okay. And now the last but not the least is the actual main file. Actual main file that pulls all three of those together into something callable from a URL. That is main.py file. Okay. Now let's slow down over here. Okay. The top of these, the top of these are the gathering tools, bringing in fast API itself. Okay. Cipher queries from queries.py, connection and query runner from db.py, and the response shape from models.py. Nothing runs yet. Nothing runs yet. This is just making everything available. Okay. Now over here, this one app is equal to fast API title graph recommendation engine is a line that actually creates the application. It actually creates the application. Every route we add after this is just attaching itself onto that one object, onto one that object. Now the interesting part, this line right above the function, this line. Let's take this one. Okay. Now this starting with at the rate symbol is called decorator, and it's what turns a plain function into an actual URL people can visit. It says whenever someone sends a request to something like recommend this, suppose here there is a name as we did in our examples features Arav. recommend rf. Now run the function sitting right underneath. Now that name inside, this name inside the curly braces is a placeholder. Whatever words show up there in the real URL gets captured and handed to the function. Okay, understandable. That's making sense, I believe. Now, inside the function itself, name comes directly from the URL. Name comes directly from the URL. Let me open my pen. Yeah. Name comes directly from the URL placeholder. Okay. And limit is optional. If nobody has specified it, it quietly defaults to 5 as given. Then the actual work happens in one line. That is run underscore query. It hands it the cipher text from queries.py plus the real name and limit that came in through the URL. Okay, so what this does, it hands it the cipher text. Okay, from where? From queries.py, from here. Okay, plus the real name and the limit, right? And the last few lines handles both the outcomes. Yeah. If nothing came back, we sent back a proper not found error instead of pretending it actually worked. Otherwise, we just return the results and FastAPI automatically turns them into JSON on its own. Understandable? Makes it clear? So, to put it all together, when someone visits recommend RF over here, FastAPI pulls RF out of URL. FastAPI, let me be more clear. Uh, so when someone visits recommend RF, FastAPI pulls RF out of the URL, okay, runs the matching query from queries.py through the connection from db.py, checks the result against the models.py. Now this flow is making clear, okay, and returns the clean JSON file and returns a clean JSON file. Okay, now this exact function answered every API call, and this is genuinely the whole app already running, already answering real requests, already answering real requests. And the glimpse of it, and the glimpse of it is this, the Fast API app. See this, the graph recommendation engine. So this is the complete project. A real graph database, 4 working traversal features, and a live API all explained file by file. File by file. The codes. Okay. So I have given a link, the codes link over here. If you want to explore it or build your own version, you can go through it. Okay. Or you can add some of your own features, you know, because I think there are still certain things which I haven't added, and the session has also got somewhat extended because I showed you real codes, what was happening behind the scenes and what was happening in front. Okay, but I would say if you clone this file, please add your own features and try to run certain things on it and show the world, loop me in for further discussion. Okay, so if graph thinking clicked you while watching this, then that's generally the whole goal. Okay, see, SQL, you can use SQL in certain projects, but if you can get a graphical view of connections, that makes whole sense, you know, in the world. Easier to understand and easier to explain someone. Okay. Thanks for watching. Thanks for watching. We'll meet next with some new topic or some new project because right now I'm thinking that we should discuss more on projects, back end, front end on AI projects. So we'll meet again. In the meantime, I would say happy learning. See you soon. Take care. Bye bye.